Hello everyone, welcome to this video entitled Maxwell's Equations in Matter. In this video we will see first the introduction. We will talk about what happens with the electromagnetic fields in dielectric materials and in magnetic materials, and finally we will show the Maxwell's equations in matter. This video has been inspired by my reading of the Feynman Lectures on Physics, volumes 1 and 2. This is a topic that I wanted to deal with, so I hope that you enjoy this presentation. In the previous video of this series, Physics number 5, we talk about the Maxwell's equations and we try to understand the physical meaning of these equations. Here we have the Maxwell equations, 4 equations. It's quite easy to remember these equations, even though they are really complex equations. Using the vectorial notation is very easy and to represent these equations in a very compact way, and also very easy to remember the equations. So today we are going to try to understand what is the effect of the matter in the behavior of the electromagnetic fields, and what is the representation of the Maxwell's equations when we are dealing with matter. So in the next slide we are going to see the Maxwell equations in matter, so pay attention to the next slide. And here we have the Maxwell's equations in matter. So, as you can see, nothing has changed. They are the same as in the previous slide and also the same that we saw in previous video. So this was a small joke just to emphasize that the Maxwell's equations that we saw in previous videos are general and are valid in any situation, also in matter. So now we can ask ourselves, what is the matter here? What is the matter in these equations? The matter is here in the charge density and here in the current density, because matter contains charges and therefore they are going to have a charge density due to the presence of matter. And also matter contains charges in motion, and these charges in motion are going to create currents. So we are going to have a current density that appears here in this equation. The other terms of the equations are just the electric field, the magnetic field, so they are not related with the characteristics of the matter itself. Before starting with matter, let's see what happens when we have no matter. If we have no matter, then the charge density is 0. So we have this equation here. These other two equations are the same. And also, if we have no matter, then the current density is 0. So then we have this equation. So this set of 4 equations are the Maxwell's equations in free space. So the conclusion here is that we can have electromagnetic fields in free space also. And one example of this are the electromagnetic waves, in which we have an electric field and a magnetic field in a wave that is traveling in free space and transporting energy in free space. For example, the light that comes from the sun to the earth goes through the free space between the sun and the earth. And these waves are generated because, as we can see in these two equations, the changes in time of the magnetic field generate an electric field, and the changes in time of the electric field generate a magnetic field. So both fields are sustaining each other, but this is another story that we can deal with probably in a future video. But then, if these are the Maxwell equations in matter, as shown here, what are all other these fields that we studied, like P, D, M, H? We're going to see this in the next slides. The first thing that we need to know is that apart from conductors that we know very well, we have other two main types of materials, which are dielectric materials and magnetic materials. Dielectric materials are formed by atoms or molecules with an uneven distribution of charge. They have bound charges but no free charges, and therefore they are good isolators. An example is shown here is the water molecule. Here in the part of the oxygen we have a negative charge in this area, and close to the hydrogen atoms we have a positive charge. So there is an uneven distribution of charge, and therefore we are going to have an electric field created by this uneven distribution of charge. One way to model this behavior is by the electric dipole. The electric dipole is an element in which we have a negative charge and a positive charge, which are very close together, and therefore they are going to generate an electric field, as shown here. This electric field is going to create an interaction with other electric fields that we have in the surroundings. And then we have magnetic materials. As in any material, in the matter we have electrons, and these electrons are moving around the nucleus, so this is generating a current. And also the electron has a spin. The electron is rotating about its own axis, which generates also a kind of current and a magnetic field. This behavior can be represented by a magnetic dipole, which is a small, very small loop of current that generates a magnetic field, and this magnetic field is going to interact with other magnetic fields that we can have in the surroundings, similarly as in the case of dielectric materials with the electric fields. So let's study first the electric dipole, which is formed by two charges of opposite sign separated by a very small distance. As shown here, we have a positive charge here, a negative charge here. The distance is d, so the distance is something similar to the distance in atoms or molecules, and we are interested in calculating the field, electric field that we are going to have in a point here, P, which is far away from the dipole. One important parameter of the electric dipole is the moment of the electric dipole, which is represented as shown here, is P equal to the charge times the distance. And here we are showing the electric potential that we can find in the books just as a reference, and then from it we can get the electric field by calculating the gradient of the electric potential, and then we will get these three equations for the three components of the electric field at the point P. And here in this diagram we have the lines of the electric field in red and the lines of constant electric potential in green. An important vector to study the behavior of dielectric materials is the polarization vector. We have to remember that in a dielectric we have many little dipoles inside the dielectric material. If the material is not polarized, then we will have that they are randomly oriented. But when we apply an external electric field, we are going to have a displacement of the dipoles. They are going to be oriented according to the electric field. So the polarization vector is the dipole moment per unit volume and is given by n, which is the number of dipoles per unit volume, times the moment of each dipole. If the external field is not too great, the induced dipole moment is proportional to the field. So we can write as shown here. This is the proportionality constant chi times epsilon sub 0, where chi is known as the electric susceptibility. And also we have to take into account that P can change from point to point inside the dielectric, and therefore the displacement of the charges will not be uniform, and this will result in a net volume charge density due to polarization. We can see this here. For example, in this part, these charges are not compensated by other charges, so we have a net charge here which is a positive charge, and in this part here we have negative charges that are not compensated by other charges, so we have a net negative charge in this part. The charge density due to polarization is calculated with this expression, is minus the gradient of the polarization vector. Now we can come back to the first of the Maxwell's equations, in which we have seen that we have the volume charge density, which is due to the effect of the matter. And this volume charge density can be split into two components. One is the charge density due to free charges, the charges that can move inside the material, for example, electrons in a conductor. And then we have the charge density due to bound charges, due to the polarization in dielectric materials. Now we can substitute the expression of the volume charge density due to bound charges, this component here, which is minus the gradient of P, and then we can use the expression that we have seen in previous slide, and we get this final expression for the first Maxwell's equation. Usually this factor here, 1 plus chi, is known as the dielectric constant of the material, K, and then this is the final expression for the first Maxwell's equation. The idea here is that we have the electric field as a function of only the charge density of free charges, which is usually the parameter that we know and that we can control. For example, in a capacitor, we can charge the capacitor externally, injecting charges into the plates, and then we have the dielectric material inside the capacitor. But what we can control, once we have selected the type of dielectric material that we are going to use, what we can control is the amount of charge, of free charge, that we are injecting into the capacitor plates. And this is all that we need in this first of the Maxwell's equations. But then we can ask ourselves, what about the field D? What happens with D? What is D? We are going to see this in the next slide. In the early years of electromagnetism, the structure of the matter was not well known. Note that Maxwell wrote his equations around 1865, while the electron was discovered much later, in 1897. So the existence of a charge density due to polarization was unknown, because they didn't have the resources to understand the behavior of the dielectric materials. And the free charge was considered the only charge that exists in the materials. So at that time, a new vector was defined to write Maxwell's equations in a simple way, and this is the electric displacement field, which is epsilon sub 0, the permittivity of free space, times E plus the polarization vector P. And using this expression, then the first equation is just assumed here, is the gradient of D equal to the charge density due to free charges. So if we consider that the polarization is going to be proportional to the field E, then we can express the displacement field assumed here. So is K times epsilon sub 0. Usually this is known as the dielectric permittivity of the material. But this is only an approximation assumed here, because if E, the electric field, is too high, D is not going to be longer proportional to E, and for some materials this can happen even with a relatively small field. So this cannot be considered a fundamental equation. This is only an approximation. The actual and valid equation is this one, which is the correct definition of the electric displacement field. But then we have another effect of the matter of dielectric materials on the Maxwell's equations, which is the polarization current. And this is a quite curious phenomenon, because even though dielectric materials are good insulators, there is going to be a current generated inside the dielectric materials. And this is so because when P, the vector P here, changes in time, there is going to be charges in motion. They are going to oscillate. For example, if we are applying here an electric field which changes in time, then the charges are going to move, maybe this one to the top and this one to the bottom, and then go back again. So they are moving, and this is going to generate a current, which is the polarization current. We can calculate this current as shown here with these two simple equations. First, the current density is the number of charges times the value of the charge, here is the charge of the electron, times the speed of the charge, which can be expressed as shown here. The speed is the derivative of the displacement with respect to the time times a unit vector in the direction of the displacement. And then the polarization vector can be expressed as shown here, is the number of charges times the charge times the distance x and times a unit vector in the x direction. So if we substitute this in this equation, then we get that we are going to have a current density which is equal to the derivative of P with respect to time. So Jp is the polarization current density and is one of the components of the total current density J that appears in the fourth Maxwell's equation. So now let's talk about magnetic materials. As we have seen in magnetic materials, we have magnetic dipoles, which are small loops of current, as shown here. These magnetic dipoles are going to create a magnetic field, and this magnetic field can interact with other external magnetic fields. So let's calculate what is the value of the magnetic field at a point P here, which is far away from the magnetic dipole. For this, we define the magnetic dipole moment, M, which is the product of the current times the area of the loop. For the magnetic dipole, we can calculate the vector potential. We can see this in Feynman's book. So this is the expression of the vector potential, and from it we can get the magnetic field by calculating the curl of the vector potential. And these are the expressions of the three components of the magnetic field at any point far away from the magnetic dipole. And here we can see a representation of the lines of the vector B generated by a magnetic dipole. So in atoms we have two magnetic moments generated by the motion of the electron. One is the orbital moment, which is due to the motion of the electron around the nucleus in its orbit, and we can calculate the magnetic moment that we have in this case very easily. The current is the charge that goes through the loop per unit time, so the charge is the charge of the electron and it goes through the loop once per period, so the current will be the charge times the period, and the period is the speed divided by the length of the loop, and then we have the area of the loop, so we can calculate the magnetic moment, current times area, and we get this expression. But usually it is preferred to represent the moment as a function of the electron angular momentum, which is given by this expression, is the vector r cross product the momentum. Here P is the momentum, the linear momentum of the electron, which can be expressed as its mass times its velocity. So we get this equation here, and finally the orbital moment can be expressed as a function of the angular momentum as shown here. And then we have the spin moment, which is due to the rotation of the electron about its own axis, and this is much more difficult to calculate. It cannot be calculated by classical physics, only by quantum mechanics, and this is the expression of the magnetic moment of the electron due to its spin, which is very similar to this one, only that we don't have the 2 in the denominator. But in the end, the total magnetic moment of an atom is a combination of many electrons in different orbits with different spins and so on. So it can be demonstrated that the magnetic moment of the atom can be represented as shown here with a factor G, which is in between 1 and 2. So the final magnetic moment of the atom is something in between the orbital moment and the spin moment. So now we are ready to define the magnetization vector M, which is the net magnetic moment per unit volume. So it's equal to the number n, which is the number of atoms per unit volume, times the average magnetic moment that we have inside the material. Note that we are interested in the macroscopic behavior of the material, so what we do is to consider the average value of the magnetic moment average over a great number of atoms. And then it can be demonstrated that the change of M in space generates a current density. So we have this current density, Jm, which is equal to the curl of M. The demonstration of this can be seen in Feynman's lectures in chapter 36 of volume 2, so you can get more information, but this is out of the scope of this presentation. So what is important is to remember that we are going to have a current density due to magnetization, which is equal to the curl of the magnetization vector. And then this is another component of the total current density that we have in Maxwell's equations. So the total current density has 3 components. One component due to the polarization in dielectric materials. The other component is due to magnetization in magnetic materials. And finally, we have the current density due to the movement of free charges in conductors. So now we can come back to Maxwell's equations, the other equation in which we have the effect of matter, which is the fourth equation. Here we have J, which is the total current density, and as we have just seen, this total current density has 3 components. The polarization current, which is the partial derivative of the polarization with respect to time. The magnetization current, which is the curl of the magnetization vector. And finally, the current density due to free charges. So we can substitute this expression here and we get this equation. And in order to simplify, a new field is defined, which is the vector H, which is defined as shown here, epsilon sub 0 times c squared times vector B minus the magnetization vector M. This constant, it can be represented, as we know, by 1 over mu sub 0. So we get this final expression for the field H. This field H is usually known as the magnetic field intensity. And now, using this definition of H in the fourth equation here, and also using the definition of the displacement vector that we have seen before, then we can finally get this equation, which is the version of the fourth Maxwell's equation in matter. So we say that the curl of H is the charge density due to free charges plus the partial derivative of d with respect to time. Finally, as in the case of dielectric materials, we can do an approximation for small values of h. We can say that the magnetization vector is going to be approximately proportional to h. This proportionality constant, K sub m, is the magnetic susceptibility. So then, using this equation in the definition of h, we can write that B is going to be approximately equal to mu sub 0 times 1 plus K sub m times h. This factor here is a constant, which is usually named as mu sub r, the relative permeability of the material, and the product mu sub 0 times mu sub r is known as mu, which is the permeability of the material. So finally, we can say that B is proportional to H. But remember that this is only an approximation for small values of H. We know that the behavior of magnetic materials is much more complex, so this is only an approximation. And finally, as summary, we have here the Maxwell's equations in matter. This is the general form in which the effect of the matter is here in the charge density and in the current density. But here the effect of the matter is hidden. So on the right we have the equations again of the Maxwell's equations in matter, but as a function of only the charge density due to free charges and the current density due to the motion of free charges. And they are also very compact, and we achieve this by adding two new vectors, which are the displacement vector d, defined as shown here, and the magnetic field intensity vector h. And these equations are in differential form, which is easier to remember. But if we know the differential form, we can think about the integral form very easily, because here, for example, we have that the divergence of d is equal to the charge density of free charges. So if we apply the Gauss theorem, then we can say that the flux of d through any closed surface is going to be equal to the total free charge inside the volume of this surface. The divergence of B equal to 0 means that the flux of B through any closed surface is equal to 0. And for these other equations that use the kern of the field, we can employ the Stokes theorem. So for example, this one here means that the line integral of E along any closed curve is equal to minus the derivative of the flux of B through this closed curve. And this one here means that the line integral of H along any closed line is equal to the total current through this curve, through this closed line, plus the derivative in time of the flux of D through this closed curve. Well, this concludes this presentation today. I hope that you find this information useful. Please let me know if you have any comment or question. Thanks for watching, and I hope to see you in the next video. Goodbye now.